Okay, this video is about the fact that if a function f has an inverse function, f inverse, then those two functions commute under composition. Remember, under composition, usually functions don't commute. But if the two functions you're composing are inverses of each other, they do commute. And not only that, they cancel out. In fact, all cancellation that you've seen in algebra is all composing a function with its inverse. So that's really important, and it's one of the most important reasons for inverses, actually. So we have this theorem. A function f is 1 to 1. If a function f is 1 to 1, then f and f inverse have the following properties. First, f compose f inverse of x equals x for all x in the domain of f inverse. Remember, this is f of x. So the domain of this thing is the values of x, and they have to be in the domain of f inverse. Why? Because you have to do f inverse first before you do f. Right? So if x is not in the domain of f inverse, then you don't get x. So this isn't y equals x. It's not necessarily the whole line y equals x, but because x has to be in the domain of f inverse, so it depends on what the domain of f inverse is. Okay? And if we now, right here, this part about f being 1 to 1, satisfying the horizontal line test, that's just saying f inverse is a function. So if f and f inverse are functions, they're actually inverses of each other, because f inverse would be f. Okay? So if I compose them this way, I get x. And if I compose them the other way, f inverse compose f, I also get x. So they commute because whichever way I compose them, you get the same thing. You get x. Okay? It's actually slightly different because on the second one, x has to be in the domain of f. And on the first one, x has to be in the domain of f inverse. But if you do the graphs, you'd see that it's they're f and f inverse. If you it's hard to compose them with a graph, so let's not worry about that. Now, this function that takes x to x, that's what f inverse does. F composed with f inverse. If you plug in a number 5, it spits out 5. If you plug in a number 8, it splits out 8. We call that the identity function. Identity function, ID, of x equals x. You get the identical thing out that you stick in. It's the laziest function. It does nothing, right? The zero function takes every number and makes it into 0, so at least it's working a little bit. The identity function, if you give it a -3, it spits out a -3. It's kind of like a machine with no mechanism. But it's a very important function. It's the identity under composition, like 1 is the identity under multiplication. 1 times something is the something, right? And 0 is the identity under addition. 5 plus 0 is 5. Here, if you compose f with f inverse, so f inverse is the compositional inverse of f. If you didn't quite follow that, don't worry too much. Maybe it'll sort itself out if you practice doing exercises and such. So, so that's just what I kind of said, right? In other words, when one composes f and f inverse in either order, the two functions cancel. And there's some real simple examples of this, which I'm going to show you here, just to make. If you're confused about a bunch of words and stuff and symbols, write things out more specifically, make up functions, make up numbers, stuff like that. So here I've got x, the cube root of x cubed. A cube root function, f of x equals cube root of x. F inverse of x would be x cubed. So the cube root function and the cube functions are inverses of each other. If you compose them like I just did here, they cancel and you get x. And we've been doing that with things before, right? But that's a really easy one to see. Here's another one. Oops, if you compose it the other direction, it looks like this. So on the first one, if I plugged in x on the left side of this first one, the first thing I would do would be to cube it. So say I put 2 in there. I cube it, and then I do the cube root. So my inside function is a cube, and the outside's a cube root. Here I've switched them. So I've got my inside function is the cube root, and the outside is the cube. Now you might say, well, which one's f and which one's f inverse? Well, the way I've got them colored, sorry, I was interrupted there. I accidentally touched my finger in the wrong place. The way I've got these things colored, can't find where my cursor is going. It's doing weird things here. F is the blue one, and the red one is f inverse. But the truth is, I could switch those and it doesn't matter. If I thought of, I could think of starting with the cube function, find its inverse, which is the cube root, and then compose them in both ways. And I always get out x. In other words, the two functions cancel. They don't give you 1. They don't give you 0. You get 1 if you're canceling by dividing. You get 0 if you're canceling by subtracting. Here you're composing inverse functions. You get x every time you do that. Okay? You get the input. Okay, so here's another one. X plus 1 minus 1 is x. This is the 1 minus 1 is 0 thing. This is what we do if we're trying to solve, say we had x plus 1 equal 5. We would subtract 1 from both sides of the equation. The reason we do that is we're actually composing the add 1 function with the subtract 1 function, and they cancel, and they give you x. Right? It's a different way of thinking about things that you're accustomed to doing already. So this would both of these would just be the left side of an equation that I've simplified this left side to this. So these composing of inverse functions we use to simplify things. Right? It's one way to simplify things. So the add 1 function. So this is f of x. Oh, the way I've got it colored, it's f inverse. Let's say it's f inverse of x equals x plus 1. That's the inside function. The outside function, g of x equals x minus 1. The blue x is this whole thing, f of x, or f inverse of x. Right, that's f inverse of x. F of x is x minus 1. So you got x plus 1 and x minus 1. You compose them, and you'll need to practice composing before that'll make a lot of sense to you, but you compose them and you get this. And I'm just showing you, we use this property to get rid of the 1 on one side of the equation if we want to. Of course, you can compose this the other way. X minus 1 plus 1 is also x, right? See? This is the same thing with division. This is canceling by dividing. So the first one is canceling by subtracting, right? The second one is canceling by dividing. So 2x over 2 equals x. Here I've got f inverse of f of x. It's like this one here. No, wait. No, it's this one. So if I plug in x, the first thing I do, because I have the parentheses, the first thing I do there is multiply by 2. That's this f inverse. And then I divide by 2. That's this f. and they cancel and you get x. So it's the f inverse is the multiply by 2 function. F is the divide by 2 function. And if you compose them, it means do one right after the other. So if you multiply by 2, then divide by 2, you get x. You get back where you started from. And same with the other way around. If you divide by 2 and then multiply by 2, you get x. The 2's cancel. Right? So this is what's going on with these composing of inverse functions. Super, super important because we use it for solving equations. If we want to solve for x, we often use an inverse function. Sometimes we don't, like if we factor something, that's a little something different. But most of the time, we actually will use inverse functions to solve equations.